turbulent flow. Again, Reynolds number, for sure Reynolds number greater than 4,000. If it's in between 2,300 and 4,000, you have to kind of use your best judgment. I would just suggest guess that it's turbulent and move forward. It's probably going to, it might happen if you do an iterative process where you're guessing, checking. So if you guess and you end up with a Reynolds number, again, in between, just assume it's turbulent and move forward. Because if it is in fact laminar, the next time through the iterative loop, it's going to be very clear your Reynolds number is going to be laminar. So I guess in most practical commercial applications, unless you're trying to maintain laminar flow, your flow most likely is going to be turbulent. So it's typically, if I'm in the transition region, it's a better assumption to go ahead and assume turbulence. Okay? Now, if it's turbulence, notice here the roughness doesn't matter. We said the friction factor is a function of this roughness and the Reynolds number. But if it's laminar, sorry, I think I misspoke. If it's laminar, this epsilon value doesn't matter. It's just a constant divided by the Reynolds number. But if it's turbulent, that epsilon value now is important. You have three options. All right, we have three options. Option A, the Cobra Equation. Now, I've noticed some of you that are leaning extremely heavy on solutions manuals or other resources will say that you use the Cobra Equation. Unless you have mathematically gone through the Cobra Equation, I would be very careful. This is not something you want to try to do on a timed exam. It's fine. It's not that hard. The Cobra Equation is exact and precise. It is 1 over the square root of f is equal to minus 2.0 times log base 10 common log of the quantity epsilon over d over 3.7 plus 2.51 divided by the Reynolds number and also divided by the square root of the Darcy friction factor f. Now what I was saying earlier is, again, unless you have mathematically gone through this equation and used it, don't try to do this the first time on the exam. This is not for beginners. Notice you cannot solve for f. Let me repeat that. You can't solve this for f. You have to iterate this. So if you're already doing an iterative process to try to find a diameter or an unknown flow rate, you're going to have to use an iterative process just on this equation by itself, meaning, and it's actually pretty simple. What you can do is you can guess a value of 1 here, plug in everything else, compute f with a guess of here of 1, and then you're going to get a value here, plug it back in there, and repeat. Within about 2 or 3 times of doing that, you're going to get a value of f. Again, you can't solve for f directly. You have to guess and check. Guess, get this, plug it back in, check, plug it back in, check, until you get the same value over and over again. And then move that value into your iterative loop for finding a diameter or something else. Normally, we just program a computer to do this. If you want to program your fancy calculator to do that, okay. Just understand if you do it wrong, there's not much I can do for partial credit. Okay. Now, you can improve this if you want to use the Holland Approximation. So the Holland Approximation does pretty good, but it's got a limited range, but it's, I don't know, I mean, it's okay. Option B is the Holland Approximation. That's 1 over rad f is equal to, or it's approximately equal to minus 1.8 times log, common log, of 6.9 over the Reynolds number, plus this quantity, it's epsilon over d over 3.7 raised to this power of 1.11. Close brackets. So log of all this stuff. So notice this stands alone over here. I don't have to guess and check here. Now here's a real simple way to do this. If you know your Reynolds number, you know epsilon over d, calculate f here. Plug it in there, and almost always you will get a very good exact value of f. Better, if you do that, solve for this, plug it in here, solve for this. you're almost always going to get a better value than you do from the Moody diagram. And by the way, I always use the Moody diagram. Right? That's how good it is. It's not great, it's not amazing, but it works just fine. It is accurate, right? But you're limited to only 2 to 3 significant figures. Okay? 3 at best, but typically 2. Modern versions of the Moody diagram are often a graphical representation of the Cobra equation. This is correct. This is often drawn from this. So this works just fine. But again, you're limited as to how precise you can get. It is accurate, just not very precise. This is precise and accurate. You can get 10 significant figures here, I guess, if you really want to. I wouldn't. It's not worth my time. The 2 to 3 that the Moody diagram gives me will be just fine, especially for a timed exam. So I guess what I'm suggesting to you is make sure you've got a method for turbulent flow approximating an F value. If you want to go the mathematical route, just make sure you are very practiced at doing so. Again, if you've relied too heavily on online solutions or resources for your homework, you're probably not practiced at this, and this will slaughter you on a timed exam. Make sure you know how to use this or become very practiced with that. Okay? If you have questions, let me know. Let's see, what else? So that is, guys, that's chapter 8, honestly. Right? You go look up your minor loss based on your system. You find F. Depending on what you have, do you have laminar flow or do you have turbulent flow? If you have laminar flow, it's pretty easy. If you have turbulent flow, you have this, okay? And we've seen this before. If you don't know the speed or the diameter, what that means is you don't know the Reynolds number, which means you don't know F. So you guess and check. Again, what I suggest is draw your roadmap. You're going to guess D, that's going to give you the Reynolds number, and epsilon over D, use that to find your F value, along with your energy loss or your head loss. Use the energy equation, and now with an F value, use that and solve for the unknown diameter, and repeat. All right? Or maybe you don't know the flow rate or the speed. And if you don't know the flow rate, you don't know the speed, and vice versa. Use the flow rate to find guess a flow rate to get a Reynolds number, and you've already got an epsilon over D, because if you don't know the flow rate, the only way you're going to be able to solve it is to already know the diameter. So you already know diameter, you already know epsilon. Now you can guess V to get you the Reynolds number, or get you the speed to get you the Reynolds number. That will give you the friction factor along with the known energy quantities. Use that to solve for your unknown flow rate, and repeat. All right? You will have an iterative problem on the exam. I always put an iterative problem on the exam. Okay? That's expected of junior level students. That's going to show up on a fluid mechanics exam. It is what it is. You'll probably have a couple of Chapter 8 problems. One of them will be iterative. The other one will be pretty straightforward. I will not put an iterative problem on the exam with minor losses, but you will have minor losses on the exam. Okay, so you will need to be able to find minor losses, but you will also need to be able to go through and find an unknown diameter or an unknown flow rate. So be prepared for one of those two. Okay? Well, be prepared for both, and it's the same concept. Okay? So work through some examples, right? Get some practice. You guys don't have any assigned homework. Right? You don't have any assigned homework. You have to turn in Chapter 11 homework today. So no assigned homework over the weekend. Focus on your Exam 3 studies. Okay? And we did talk a little bit about drag forces. right? Drag force is equal to 1/2 a coefficient of drag, density of the fluid, front-facing area or projected area facing into the fluid that's moving, and the average speed squared. Okay? Now when you look in, you guys can hear a pop here, sorry. When you look in the text, right, make sure you read the top of this table and know the conditions when you can use these values. But what I did want to show you is some of these common shapes, they'll give you, like for the average person here, right, for the average person, they're giving you the product of the coefficient of drag and the area. So sometimes you'll have that. They'll give you coefficient of drag and the area independently, or in this case as a product. So make sure you read the table and understand what it's giving you. Is it giving you just a coefficient of drag, or is it giving you the coefficient of drag and the area? Sometimes you'll get both. Okay, so just be aware of that. So go into know where those tables are, have access to those, be able to get to those. Basically, here's my philosophy on problems like this, kind of like with the buoyant force in the first exam. You guys, this is like the third or fourth class where you've encountered forces before. To just plug and chug into a formula and give me a force, that's not enough, right? You need to be able to do something useful with it, right? By the way, if, I don't think this has come up before, but if force and speed are constant, this is an old physics 1 relationship. If force and speed are constant, then power, right, which we sometimes call W dot, or work rate, is just force times speed, right? Because work, or energy, is force times distance. Power, which is a work rate, is force times distance per time. So if force and speed are constant, if I've got a drag force and a constant speed, then the power is just simply equal to the product of force and speed. Okay, so just be aware of that. The reason I say that is, again, plugging and just here's an equation, plug and chug, find me the force. That's a little too simple for junior level engineering students. It most likely is going to be find the force and do something useful with it. A common useful thing you can do with it is to figure out how much power, or knowing how much power, figure out how much speed is required, or some combination thereof, right? Given a force, do something useful with it. Again, this is not the first time you've encountered forces. If it is, you are in the wrong place. It's not unreasonable for me to ask you to do, here's enough information to find a force. What's something useful you can do with it for me, okay? That's it. Some of you guys, well, between thermo and between this class, I've had people get in trouble on the exam, on the previous exam. Be sure to read syllabus about doing your own work on exams. If more than one of you turn in the exact same solution to me, I will not grade that problem. If you give me verbatim information from an internet resource, you will likely get a 0 for the entire exam. Okay? It's one thing if you're using things as a tool, but if your only ability is to copy something, maybe change a couple of numbers, you're not an engineer. You're in the wrong place. You need to be able to formulate your own solutions and then check them against other sources and make sure you're on the right path. That's okay. I'm not going to police that. But again, make sure you know what's going to get you a 0 or not. Don't complain to me after I give you a 0 because you didn't know the rules. Know the rules. That's your job. Ask me if you have questions. All right, guys. Have a good one.